what's the difference between predicting a sequence of words with the beginning symbol before them or after? If this is the first thing in the training, in the test set that you're trying to predict, if you're trying to predict W1, you don't have any context, you will back off from a foregram to a trigram to a bigram to a unigram if you're using a backoff model. And you will basically provide as an output the estimate based on a unigram that doesn't require any context. If you have this symbol, it gives you some context. So we're here, we're trying to predict W1. We can't use a foregram, we can't use a trigram, but we can use a bigram. The conditioning event for the bigram would be the beginning of sentence symbol, which means the bigram will be trained based on all contiguous occurrences of this beginning symbol plus a word after that. So it would be related somehow to the count of the number of times beginning of sentence symbol was followed by W1, divided by the count of how many times beginning of sentence symbol was seen alone. So in practice, it could make a big difference. It's asking how common is W1 in general, regardless of where it occurs, versus how common it is as the first word of a sentence. And the two could be quite different, right? That's one difference. The second thing is, as you go towards the end of a sentence, you hit an end of sentence event. I'll write it like this, end of sentence event. And the probability of the entire sentence consists of a product of going from the first word, given all the words before it, which is beginning of sentence symbol through Wi minus 1. So this is general case, I goes from 1. Right, so we start with predicting W1 with just this context, when the rest of this is empty. And then we continue with the second word with this context and so forth. And the question is, how far do we go? Well, I say in this case we go to 9, and end of sentence is effectively word 9. We treat it as a real event, as a real word, and the reason again is one of modeling. If we stopped here, we are answering the question, what is the probability that the first 8 words of a sentence were these? But not necessarily that the sentence ended there. Right? There could be another sentence that goes beyond W8 and continues with other words. It's a different event. I'm interested in the probability of the entire sentence, which means it starts here, and this is the last real linguistic word, and therefore there's an event that says that's the end. So these things do make a difference. Now, one could argue that if you're looking at the probability of an entire corpus, it consists of one sentence after another, you will notice using this notation that every end of sentence is followed by a beginning of sentence. And then you have W9, W10, and then end of sentence, and then another beginning of sentence, except for the very last one. So you could be tempted, if you really treat these as words like any other word, this transition has probability of 1 effectively. Right? Which is why we don't really include this one. We don't include this in our probability stream of what we're predicting. So I call this context Q. This is just a term I invented. It gives Q, it gives some information about the context, but it's not something to be predicted itself. Alternatively, you could choose to just combine these two into one thing, call it a sentence boundary, or call it whatever you want, and just decide that there are boundaries and they are part of the vocabulary. That would be a fine thing to do. And then the sentence boundary would both be something you're predicting. You're saying now comes the end of a sentence, and of course it's also a beginning of the next one, and it also becomes part of your context. That would be a fine thing to do. And if you were to create your own toolkit, if other people created their own toolkits, they might have gone this way. I chose to go the way of separating the two because A, it allowed me to think about it more clearly. that these are two different issues. One of them is a context, the other one is a real event. And also because it allows me to throw into the training data partial sentences. Right? I can throw into the training data sentences that have a beginning but not an end, or an end and not a beginning. So the bottom line for playing with the toolkit is that you should use only a single context queue, and that should be it. There could be other context queues, and I give examples in the documentation. For example, beginning of paragraph or beginning of whole document. If you believe that words at the beginning of a whole paragraph are different statistically from words at the beginning of a sentence which is not a beginning of a paragraph, you can include indications of where the paragraph begins in your corpus. So the corpus would look something like this. Beginning of paragraph, beginning of sentence, blah, blah, blah. End of sentence, beginning of sentence, blah, blah, blah. And at some point there would be another beginning of paragraph here. Is it clear? Yeah.
So what is the condition in the trigram probability for W9?
Good question. So it's somewhat arbitrary. Currently in the implementation in W9, it's these two. And you could argue that really they should count as one event, not as two events, and go back one more. It's somewhat arbitrary. There's nothing wrong with deciding to stop here because there's nothing about the trigram that says how you define words or events. I actually like this because it prevents me from considering the word that occurred before, because I don't believe that the last word of the previous sentence has that much to say about the first word of the next sentence. And in fact, I think I may have a flag in there that says, no matter how long your n-gram is, cut the context of the sentence boundary. Because that's a modeling decision. It's not a statistics decision. I believe that there's not much information beyond that, and I'd rather cut it there.
But you're not modeling one of the sentence boundaries, the start of the sentence.
No, I never try to predict this, but I do use it as part of my context. So you will see in the trigram, in the count files of the toolkit, you would see things like end of sentence, beginning of sentence, the occurred 38,000 times. End of sentence, beginning of sentence, of occurred this many times, and so forth. You will see these counts of how many times these triplets occurred. So I apologize again for the temporary confusion. If it caused you hardship and you need an extension, just let me know. Send me email.
I ran the experiment on both versions actually.
Okay. That's good. That's even better.
So with the correction, adding two context cues, the perplexity scores consistently degraded like a huge amount.
Yeah, it's kind of not fully defined comparing them, because if you make this end of sentencing a context cue, that means you're excluding it from the vocabulary. And if you compare perplexities of two models on different vocabularies, the comparison is not kosher, especially when one of the words is a very common word. The end of sentence symbol is one of the most common words. It's probably the most common after the word the. Right? It's a very common word, so excluding it changes the picture. But I'm really glad that you experimented with it. That's the thing to do. That was the whole purpose of this assignment, is for you to play with it and get a feel for it.
So having end of sentence, beginning of sentence as the context would treat the at the beginning of the sentence in the middle of the document differently from the at the beginning of the sentence at the beginning.
Yeah. Yeah. Somewhat differently. Not very differently, because the at the beginning, because you actually no, I think I cheat and I pad the context with end of sentence symbols. Yeah, I do that. So you could make other decisions when you implement your own code, but but you need to understand what you're doing so it's consistent. I should warn you that deciding on the vocabulary and how to compare things and what's in the vocabulary, what's not, looks like a stupid little technical detail, and it is a stupid little technical detail, but it's really important to get it right. Otherwise, you get very weird outcomes. Hopefully, what you're learning is that how this represents sort of information theory, and if you start from the information theory concept, you will hopefully do things right. Okay, so back to our business. We're going to talk a little bit more about information theory and then switch to decision trees. So I'll summarize everything I wanted you to learn about information theory, or almost everything, very succinctly. We have the notion of surprise, and that would be I, according to model M, of some event which is defined as, I'm not going to give the formulas, but just the concepts, the amount of surprise, amount model M or distribution M is surprised when experiencing an event. And now we have this thing called cross entropy, which is really the fundamental quantity. Cross entropy between some distribution and some other distribution. M is the expected surprise of M in the face of events from P. Before we get too far, let me call this T for true. Events from T. So this is defined with regard to any two distributions, but I like you to think about it as this is the true distributions of the world, and this is the model or the approximation of the world. So this is the expected surprise of your approximation in the face of events that come from some true distribution. And then the special case of this, or let's say the entropy of T, is the special case of the cross entropy from T to itself. So this is the expected surprise in the face of events that come from T by a model that knows T. That's not an approximation, it's the exact thing. And we know that this is less than the cross entropy from T to M for any M. That's the fundamental statement here, that the average amount of surprise is lowest when you know the truth. And in fact, it's not equal, it's strictly less. It's only equal if they are exactly the same. So I'll make it for every M not equal to T. And then I can say strictly less. So you can call this the inherent surprise I'm not being very consistent here, in T. And this inherent surprise is what we'll call the information. So when I first introduced it, I loosely equated surprise and information when I talked about log of 1 over P. But I think it's more accurate in the analogy to say that this is the surprise. This is a subjective measure. Whereas I will reserve the word information to describe the objective measure. So just because you have if you have a bad model of reality, you're going to be surprised a lot. That doesn't mean you're getting a lot of information, which means you keep getting surprised because you're holding the wrong model in your hand. If you have the perfect model in your hand, the truth, then what you get is pure information. How can you get pure information if you're holding the truth in your hand? Well, the truth that you're holding in your hand is the nature of the stochastic process. It is not what actually comes out of the stochastic process. What comes out of the stochastic process is to some extent chance. And the information you get is about what chance event happened to happen. And then we have the other important measure, which is, well, let me first start with KL. The KL distance from distribution T to distribution M. And of course, it's defined for any two distributions, but I like to use the letters T and M. Is the difference between the cross entropy from T to M and the cross entropy from T to itself, which is the entropy of T. Which is, it's the difference between the average amount of surprise that M experiences and the average amount of surprise that T experiences when they're both exposed to events from T, which means it's the difference between how much surprised you are and how much surprised you could be, the smallest amount possible. So in other words, it's a measure of the unnecessary added surprise. Right? Unnecessary as opposed to inherent. Sorry. Additional price. Or in other words, it's the distortion. The amount of distortion in M relative in the model relative to the reality. Now, distortion can be measured in many different ways. There are many types of distortion. But this is one particular type of distortion that is most natural in the context of information theory. It has to do with how much you distort the log probability rather than how much you distort the probability. And then the other thing we discussed was mutual information. I'm not going to repeat that. That's a useful concept. I won't repeat it, but I'd like to do some math with it. I guess before I do that, any questions about the concepts above? Any comments? Please.
So which one of these concepts can be stated as the likelihood of uncertainty in the model?
The likelihood of uncertainty.
Sometimes in the discussion of entropy, it's defined in terms of the amount of information, and sometimes
Right.
something is said about
Okay, the amount of uncertainty, not the likelihood of uncertainty. That.
I'm not sure. I think I read something about the likelihood of uncertainty.
Okay, I'm not sure what that means. I don't know what the likelihood of uncertainty is. But the amount of uncertainty would be here. Of uncertainty in T. The amount of uncertainty in the distribution T. Likelihood of uncertainty, if I was forced to interpret what that phrase means, it would be if you're trying to estimate the true entropy of a process and you don't know it because you only have data to estimate it from, then different answers would have different likelihoods. I'm not sure that's what they mean. If you go back and point me to it, I'll try to figure it out. But this is actually an important point, that everything we did here falls into the side. If you remember the big picture I drew early on in the semester of an arrow going from parameters to data and then from data back to parameters, and going from parameters to data was probability theory, and going from data to try to infer something about parameters was statistical estimation, right? All of this goes in the direction of probability theory. Namely, we've discussed a situation where we know, at least we as analyzers, know what T is, what the truth is, and somebody else has a model M in their hand, and we are assessing you know, how far they are from the truth and all of that. But we're assuming here that there is a known distribution T. There's a completely separate theory about how do you estimate entropy if you don't know it. How do you estimate it from a sample? So if I have a die in my hand, 6-sided die, and I flip it, and I want to know the entropy. If I know the probability of each face, I can calculate the entropy, right? But if I don't know the probability of each face, I can estimate it by collecting a sample, and the estimate has some variance, and for every point, every possible answer, it gives a different value to the entropy, so I will get a distribution over all possible entropies. And as you can imagine, the larger the sample, the more accurate my estimate would be, the smaller the variance. But you can think about it then as the entropy being a random variable that is a function of the parameters that you're trying to estimate. Yes?
What's the relation between cross entropy and neutral information?
So cross entropy of T and M is sum of P sub T of X times log of 1 over P sub M of X, sum over all X's. Okay? You can also think about it as the expected value according to T of log of 1 over Pm of X. Mutual information between what? I'm trying to find a relationship I'm not sure I could find.
Cross entropy is between two models.
It's between
of the same random variable.
Right.
That the mutual information is between two
Thank you.
random variables.
Thank you. That's a very good way of convincing me that there's not much relationship. Yeah, this is about relationship between two distributions of the same random variable, which is X here. This is a relationship between two random variables under a particular distribution, say P. So a joint distribution over the two, a particular joint distribution over the two. So not much relationship, nothing that I can think of. Okay, so let's focus now on, yeah.
Sorry to
good.
just get off track again.
That's fine.
In the cross entropy of like your true distribution in your model,
Mm-hmm.
isn't your model trying to, well, you're trying to model the true distribution. So, but are you coming to the table knowing that they don't have the same distributions?
I'm coming to the table assuming that they're not necessarily the same.
Okay, and with mutual information, you come to the table saying these do come from the same distribution. They come from a joint distribution.
Well, the joint distribution defined in terms of two different variables. It's a joint distribution over two different spaces. So you can think about it as a table of a joint probability of two events.
So does it not make sense to try and have the true distribution be a random variable because it's not really a function, it's just sort of a constant?
I don't fully understand, I'm sorry.
So with mutual information, you have two random variables.
Okay.
And with cross entropy, you have it's usually between like a true distribution and a model. So the model could be a random variable because it would be dependent on the data that you see.
Okay.
But
This is fixed, you're saying.
right. Okay, yeah, so since your true distribution
And this is a random variable, it depends on the data. Okay, that's an interesting way of thinking about it.
So then it wouldn't make sense to take.
But this is fixed. If this is fixed, there's no point, there's no meaning to taking much information. But it's interesting to think about this as a random variable. If you derived a particular algorithm or model that takes data and converts it, a particular estimator, particular maximum likelihood estimator or some other kind of estimator, then it's a random variable. It depends on the data. Yeah, think about it.
So what if you're Bayesian? Then then your true distribution is not fixed and it's also a random variable.
Yeah, that's true.
So do you think that somebody could try and make an argument from a Bayesian perspective that you could have mutual information?
Oh, absolutely, absolutely. I mean, you can think of the cross entropy as something you're trying to estimate. You're trying to estimate the real, some kind of, or try to estimate the entropy of T and start with a prior over T that gives you some distribution over the entropy, its entropy, and then, yeah, you could play with it. Yeah, that's cool.
One direct difference which you can see between cross entropy and mutual information is that cross entropy is directional, whereas mutual information is.
Yes, it's true that cross entropy is directional, mutual information is not, but let me emphasize that there are very different creatures. One of them is a function of two distributions, a directional function of two distributions, and the other one is a function of two random variables under a joint distribution, is the point that Hyun made. So yeah, that is a difference, but they are very different creatures, so there are bigger differences yet. Okay. So, you all know the chain rule. Chain rule says that P of x1 through xn can be written as P of x1 times P of x2 given x1, P of xn given x1 through xn minus 1. And it doesn't have to be in that order. It could be in any order. There's a similar rule that applies to entropy. So you can think of the joint entropy of x1 through xn. These are all different random variables now, so it's like x, y, z, w, and so forth. Can be written as the entropy of x1 plus, so that's the difference here. This is product, this is sum, because remember entropy is in the space of log p's, and log p's are additive, plus the entropy of x2 condition on x1, on knowing x1, plus the entropy of xn condition on all the x's 1 through n minus 1. Again, to remind you, these indices are for different random variables, which we normally called x, y, z. I just wanted to write it in a more general way. So more specifically, h of x, y, and z can be written as h of x plus h of y given x plus h of z given x and y. And you can see it from the picture. H of all three is this union, and it be calculated as first this one, this is x, and then if this is y, h of y condition on x, so it's this part, and then this is z, this part is h of z condition after you took a bite of both x and y. So it's just an easy way to think of this calculus of entropy, is that you can break it down, and of course the chain rule could be applied in any order. So now think about, you're trying to learn a function y. Learn y using features which I will call x1 through xn. So I set apart y, but it could be really thought of as one of these. I just called it a different letter, but we have a whole set of random variables, and I'm trying to learn one of them using the others. And my assumption is that the mapping is not deterministic. Namely, that if I'm given specific values for all these random variables, it doesn't determine for me a specific value of y, it determines for me a distribution over y. So I'm effectively trying to learn a conditional distribution. P of y condition on x1 through xn. So this might be the case in any language technology field when you're trying to learn, let's say, the topic of a document. Y would be the topic, and the axis would be either every word in the document, or every word in every position in the document, or any other feature. There could be thousands of them. There could be millions of them. Or if you're trying to learn translation, Y could be the sentence in the target language, and the axis could be any aspects of the source sentence. So X's are your inputs to the language technology problem, and Y is your output. And the important difference here is that we're not thinking of a deterministic output. We're thinking of a distribution output. Given all the values of X, you get a distribution of Y. Ideally, you would like that distribution to be as sharp as possible. Namely, you would like for most values, combined values of the axis, of the features, of the inputs, you would like ideally the output to be a conditional distribution that's peaked around one particular value of Y. You want one sentence that would be the best translation, or one topic that would be the best match for the current document. But you might accept a situation where there are two reasonable answers. So most of the distribution P of Y given the axis would be peaked not around 1 point, but around 2 points or 3 points, or a small number of points. But in other words, you want this distribution, if you think about a distribution over Y, to have low entropy. Ideally, we want the conditional entropy of Y conditioned on x1 through xn to be as low as possible. Usually you would think that if you used all of the features, you would have the best, lowest remaining entropy. And that makes sense if this is your Y, and the x's are all over the place. They could be big, they could be small. They're features. You want to take as many bytes out of the Y as possible so that you're left with the least amount of remaining uncertainty, right? And that is true if you had infinite data, or if you knew the true distribution of X and Y. But in reality, you have a finite amount of data. So every X that you add in is based on the sample. And furthermore, it may increase your computation. So you may be in a situation where you only want to include a handful of features. Maybe you only allow yourself 1,000 features out of 1,000,000 that you have. It could be for computational reasons. It could be for sparse estimation reasons as well. So the question is, which features should you choose? And this is known as the feature selection problem. The feature selection problem is defined also outside the context of information theory, where you have a target function Y, which is some function of the inputs, x, million. And we believe that it's really a function of only a small number of them, and we're trying to find out which ones. And in this context, in the general context, it might be thought of as a deterministic function. In the real world, it will not be deterministic functions for several reasons. One, it might depend on features that we don't have or we didn't think about, like features that are outside that we just didn't capture. Or it might be inherently stochastic. It might be inherently has some elements of chance in it. So we're not going to try to find the correct deterministic function. We're just going to try to minimize the conditional entropy. So goal, minimize conditional entropy. formula, find the argmin of entropy of y conditioned on xi1, xi2 through xi, say 100, over all indices I1 through I100 between 1,000,000 and 1. In other words, choose 100 indices between 1 and 1,000,000. Choose the 100 features that you want to include that would give you the lowest entropy. So the number 100 came from the outside, maybe from considerations of computation or of some prior belief about how this function really works, or from anything. But the problem is not combinatorial, because there are 1,000,000 choose 100 possible solutions to consider in the minimization, right? And that's about in the order of 10 to the 6 to the power of 100, roughly. So that's a large number. We can't, given the fixed training data, or suppose even somebody gave us the full correct function, suppose we could calculate this value immediately in one machine step for any particular set of 100 features, we still could not realistically go over all possible sets of 100 features in real time. So we need a heuristic algorithm for finding it. So we might, so the natural thing to do is greedy solution, greedy search. How would we do the greedy search? We will start by choosing the one most informative feature. And after we include that one most informative feature, we will look for the next most informative feature, and so forth. For example, we can rank all 1,000,000 features in terms of by the mutual information between y and that feature. The one feature that has the highest mutual information is also the one feature that has the lowest conditional entropy when you plug it in here, right? That's the same thing. I hope you know that. Mutual information between this and this is, maximizing that is the same as minimizing the conditional entropy of y given that x. Let me write here explicitly that the thing that minimizes over all the i's, I1 through I100, the conditional entropy of y given xi1 through xi100 is the same thing that maximizes over same indices I1 through I100 the mutual information between y on one side and xi1 through xi100 on the other side. Because these two are related to each other through the entropy of y. So when I talk about minimizing the mutual conditional entropy, it's the same as talking about maximizing mutual information. So I'm going to go to my greedy process. I'm going to start by calculating the mutual information between x and any one of these x, between y, any one of the features individually. There are only 1,000,000 of those, so I only need to do 1,000,000 calculations, not exponentially many calculations. And then I choose the winner. Let's say the winner is, let's say the best one is x37, first place. And let's say x53 is the second place. and so forth. I can rank all of them. So I can now be tempted to include the top 100 features from this list. Would that solve my problem? If I just took the 100 most mutually informative features with y, does that solve my problem?
I think you need to run the whole thing again on the remaining 900.
Why? Why not just choose the top 100?
Those top 100 may all share the same mutual information.
Right. They may overlap. Like x37 and x53 might be very, very similar to one another. So the picture to have in mind is here's y, and here's x37, and here's x53. So they overlap so much that after I added x37, adding x53 does not add that much. Right? So this comes about because mutual information is not additive. The amount of information you get from one random variable on another, in this case x37 on y, plus the amount of information you get from a third random variable, x53 on y, does not equal necessarily the amount of information you get from the two of them together about y. All right, so I'll write it this way. I'll write it in terms of x and z. I of the mutual information between y and x and z together is not necessarily the sum of the mutual information between y and x and the mutual information between y and z. X and z could provide similar information. Info about y. In the extreme case, if it turns out that they are actually calculated the exact same thing, and they were included by mistake, they both will look top choice. But once you included one, you gain nothing by including the other. So another analogy would be if you consult experts. You may be willing to pay $1,000 to consult one expert, and also $1,000 to consult another equally good but different expert. But if their expertise are very related and very similar, you may not be willing to pay $2,000 to hear from both of them because they're going to tell you similar things. Right? So this is a very common occurrence, that the amount of information provided by different features overlap. But I should add that the opposite could happen too. That the amount of information that, I think we discussed that maybe last time, the amount of information that is given to you by two experts together might be more than the sum of the information from each one of them alone. That is less intuitive, but it certainly can be true. So an example of that I think I gave last time was the keys in a safe. If you think of the key you have a safe with two different locks, that require two different keys. And if you think of the amount of information that each key gives you as the value of that key, the value of one key by itself you could say is 0 because you cannot open the safe. The value of the other key by itself is 0 because you cannot open the safe. But the two keys together are worth a lot more than 0 plus 0. That's kind of a hokey example. But if you want a better example, you can think of two parts of a password. Each part by itself is not enough to crack, to log in, but the two halves together are. And these are all extreme cases, but they're also grayscale cases, where you can think of Sherlock Holmes and pieces of a puzzle fitting together, and each piece by itself is not enough, and the two pieces are enough. I can think of other examples. It is true that this situation can happen, although in the real world, this situation is much more likely. So what we will say here is that it could be greater than, it could be less than, or it could happen to be equal. The much more common case is this one, which is that consulting the two experts together doesn't give you as much information as you would hope if they gave you completely independent advice about why, or completely non-overlapping is the right word. So this corresponds to overlap of information. So now we go back to our problem. If this was an equation, if this were an equation, we would just take the top 100 here and it would be done. But because it's not, and because once you choose the first one, the amount of information in all the others could go up or down, we will need to do as you suggested and recalculate. So we run this just to find the first feature to implement, and then we choose that x37 and incorporate it, incorporate the winner with the winner. And by incorporate we mean we decide to bring it into our model, and therefore now h of y went down to become h of y conditioned on x37. And now we're going to find our second feature by saying second feature is going to be defined as the one that, I'll use it in terms of max, that maximizes over all features. I goes from 1 to 10 to the 6, but of course not equal to 37. Exclude the one that was already chosen. I'm going to find the one that maximizes the mutual information between y and xi conditioned on already knowing x37. And of course this is the same as writing argmin with the same conditions of the conditional entropy of y conditioned on x37 and xi. These are the same, exactly the same setting, same condition. And to do that, I again need to calculate the value of this, or of this, it's the same thing, for every one of my 999,999 remaining features. I calculate them all, and I look at the one that's the highest value, and it turns out it's no longer 53, it's 170. So now I incorporate 170 in, and now I rerun everything else. So 170 is going to make its way into here and here. And it's going to be not the second, but the third. So at any point, I will take the features that I've already decided to accept, keep them fixed, conditioned on them, and look for the mutual information of any one of the remaining features with regard to I, conditioned on knowing these values. How much calculation am I doing here? Order of 100 times for the 100 features, times the number of features I'm going over, 10 to the 6. That's a large number, but it's still much smaller than searching over all possible subsets of size 100. Right? Is this guaranteed to give me the right answer? No, it is not. This is a greedy stepwise optimization. It will not necessarily find the set of 100 that has the most mutual information. It's likely to give me a decent set, but it's not guaranteed to give me the best one. Specifically, if there are two features, x200 and x305, that love to go together. The two of them together give you a lot of information about y, but each one of them alone doesn't, which can happen. They may never be chosen in the top 100 because they're not very promising on their own. For example, suppose y is pretty much the XOR of these two. Then if you knew that, and you included these two in your model, you'd be done. But if you don't know that, neither one of these two on their own would seem like a very good feature. Except if you're lucky and one of them got included, then the other one all of a sudden would look great. Right? because it'll give you a lot of information. But until you hit, if you didn't include one of them, you will never know it.
So if you suspected that you had features like that,
Mhm.
you could just tweak the algorithm.
Great, great. How would you tweak it?
Well, or tweak it, you would do just a double loop overall.
Right, so instead of a greedy one step, you do a greedy two-step look ahead, right? You will calculate this. I'll erase this because I want you to think in terms of mutual information, but remember that they are the same. Let's say we already chose 37 and 170. Now we are going to look at all pairs. Mutual information between x and between y and xi, xj. I'll consider incorporating two at a time, and I will look not just for I, but for j as well. For some 2 I and j's between 1 and a million, two values that maximize the mutual information condition of what have already been incorporated, right? Will that work to take care of the problem of XOR of two variables? So if y was really an XOR of two variables, will it find that?
I don't think so. I think you have to just explicitly include pairs. I mean,
Well, he is considering pairs here.
Oh, well, I mean, sure, that would work, but I mean, like, what you could just say, would it be a problem where it was, like, it was exactly determined by three variables, three features?
Right. So the answer to my first question is yes, it will solve the problem of XOR of two variables, but it will not solve the problem of XOR of three variables. If y were to a great extent determined by an XOR of three variables, any two of the three would look useless until you found the third one. And you're paying a price here. Instead of doing 100 times 10 to the 6, you're doing 100 times 10 to the 6 choose 2, or maybe 50 times if you do it in pairs. But in every step now you're considering all pairs over a million, which is a much bigger deal. So you're doing sort of a quadratic search instead of a linear search. You are getting rid of the problem of pairwise XOR, but not of three-way. Of course, you could do three-way, and it'll cost you triple that amount, but you didn't answer the four-way. So the full 100-way is intractable. You need to do exponential amount of work to solve it, unless there's something about the problem that could restrict the solution. You know, there's a shortcut. But in the general case, there's no way of doing that. So we run into things like that a lot in language technologies. If you build an exponential model, which we will discuss in class, you have to choose features. And how you choose them, it's computationally expensive to choose them, and you have to keep in mind that it's a greedy process, and that combinations of features might have more or less value than otherwise. When we discuss decision trees, which we're going to do in a few minutes, it's the same problem.
How do we know how many features do we want? Like, for example, this 100, why do we want 100, why not 200?
If your limitation comes from computation, then it's up to you to decide how much computation you can support. If your limitation comes from the finite amount of data, then in principle, each one of these individual mutual informations between y and an individual x is not difficult to estimate because it's only xi. But once you have, I'm sorry, this is semicolon. But once you have a conditioning on lots of other x's, now to estimate this, you're basing it on less and less data, right? So it's like any other kind of model where the more parameters you have in the model, the less good your estimate, the higher the variance of the estimate. And it's a trade-off between the bias and the variance. As you increase the number of parameters, you're reducing the bias, but you're increasing the variance. And how do you do it in practice? Well, leave one out data, right? Or not leave one out, but held out data. Because what we discussed here is the theoretical case where you know the function and it's just a computation problem of finding the 100. But in practice, you don't know the function. You're basing it all on estimates. Estimates derived from the data. And when this conditioning thing includes many, many variables, the estimates are based on less and less data, and they are less reliable.
So can we make this algorithm, this greedy search, we set a threshold when there are too many features, so that there will be less amount of data, and if this threshold, this threshold will be the amount of data available for this feature set.
That's a very reasonable heuristic, sure. Fatma?
If we know that the selected features are independent, would the naive greedy approach work?
What do you mean by independent? Independent of one another?
Yeah, like they're independent random variables.
Okay. And they're also independent of y? No, they're not independent of y, because otherwise they don't give you any information about y. So it's a good question. So if they're independent, it means they don't overlap, right? So they're all different.
In that case, you could just select the first 100 directly.
I would think so. But that's if you're assuming they're pairwise independent. But features can be pairwise independent and not three-way independent. And not four-way independent. So there's a stronger sense of independence. I forget what the term is. Mutually independent, or when any subset of them are independent of any other subset. That's the strongest form of independence. And under those conditions, you can just choose the top 100. Under the condition of just pairwise independence, you can probably choose 2 at a time. That's my guess. Not sure.
That's probably not realistic in NLP.
No, not realistic. And it's not realistic to know, even if they were independent. How do you know they're independent? And in the real world, of course, nothing is independent. Everything is a little bit of dependence, right? But it's still a useful observation, because we're not looking for optimal solutions. We're looking for good solutions or decent solutions. And if you have reason to believe that they are independent, then you might think this method is good enough, the heuristic greedy. And if you have reason to believe that they are highly dependent, then you want to keep recalculating every time.
Why don't we cluster all of features together, like into separate clusters, and based on the mutual information between each other? Say x1 and x2, if they have high mutual information, then we push them into one cluster, and then out of the separate cluster.
Right. That's an interesting idea. Pre-calculate the mutual information between any 2 features, and use it to form clusters. The problem is now you have 10 to the 6 squared. That's a lot of calculation. You don't have to pre-calculate all the distances. You're right. You can heuristically take one, find the one that's closest to it, so that's only order million calculation, then find another one, and yeah, you could do also heuristics. That's a good point.
Within a distance threshold, like find how many points are there.
Right. Right. And mutual information might obey something like a triangle inequality, in the sense that somebody who's close to me is far from somebody who's far from me. And somebody who's close to me and another person is close to me, they too are somewhat close to each other. Possibly, I don't know for sure. But you could imagine using something like a triangle inequality to reduce the amount of computation you do. So yeah, there's a lot of room for heuristics here. Okay, that's all I wanted to say about information theory, unless you guys have any more questions or comments. Okay, so let's talk about trees. Decision trees were invented in the 80s. I think 84 was when a book actually came out by 4 statisticians from Stanford called Classification and Regression Trees. And the idea was to have a formalism for a some kind of a decision procedure based on a lot of features that can do either regression or classification. So I'm not going to teach decision trees. I assume that you kind of know what they are. But the idea is that you have an output y. You have an input that consists of lots of features. There could be, I don't know, a couple hundred or 1,000 of them or even more. The features could be binary. They could be numerical. They could be more complicated than that. They could be categorical. And then a tree would look like here's the root of the tree. And in the root would be one of the features, x sub, say, 37. And you ask some question about it. If it's a binary feature, the question, there's only one question you could ask. Is it on or is it off? Is it yes or is it no? Is it 0 or 1? If it's a more complex value, you ask some binary question about that complex value. If it's a continuous number, you ask is it greater than or less than something. Or if it's an integer, you can ask if it's prime or not. It could be any binary question you ask. The important thing is there are two possible answers, yes and no. And then based on that answer, you ask another question, maybe on x3, and here you could ask on x7. It doesn't have to be the same one. And again, you ask some particular question about them. And you keep asking questions, and at some point, not necessarily all at the same depth, you provide an answer. And the answer would be the value of y. Now, what would the answer be? If it's a number, that's called regression, right? Mapping from some space of x's to a continuous number is called a regression. So if the output is a single number in each one of these leaves, that's a regression tree. If the output is a class or a category, that's called a classification tree. So together, classification and regression trees, C-A-R-T, these trees are known as CART. The only difference is it's not in the X and not in the questions to get asked, it's in the output. If the output is categories, it's classification. If it's numbers, it's regression. So there's a whole theory of how to build these trees and how to use them and how to smooth them and prune them and trim them and all of that. And all that was developed in the few years after the paper came out, so in the mid to late 80s. And then in 89, a group of language modeling researchers at IBM thought of using the same structure of trees, not for classification and not for regression, but for the third thing. Do you remember what it is? The three things that we do: classification, regression, and density estimation. Right? Classification is mapping the x's to categories, C1 through CK. Regression is mapping the inputs to a real number. And density estimation, in fact, what they did was not regular density estimation, but conditional density estimation. Conditional density estimation is mapping the same inputs into a distribution over y conditioned on these inputs. So in other words, given the same inputs, this gives you a category, this gives you a number, and this gives you a distribution. And you can imagine it's very easy to take the tree and to put a whole distribution under each one of the leaves. Instead of a single number in each leaf, you put a whole distribution. The distribution could be continuous, or it could be discrete. In the case of using this for language, it's a discrete distribution over the vocabulary. So what they try to model with this thing is the probability of the next word given the history. Remember, we use H for the history, everything that happened before that word. Viewed this way, this is kind of like an n-gram, except without restricting in advance the size of the n-gram. It's like a variable length n-gram. You look at the history, and you answer some questions about the history, and at the end, you provide the distribution over W condition on that history. So these questions, instead of being about specific features, are generic questions about the history. So we can call it This would be Q1 as a function of history. The important thing is that the question takes as input the history and produces as output yes or no. And this would be a different Q. Q7, regard to history. Q35, regard to history, and so forth. So a language model tree is a tree that takes history as input, percolates it down based on the questions to a particular leaf, and then provides, in the leaf it finds a distribution over words and provides that as the distribution of the next coming word condition on that history. A language model tree could be a good thing, could be a bad thing, but that's what it is. So there are a few questions that come to mind when you think of using trees to model language in this form. One is, what set of questions should you consider to build a good tree? So that would be number one, would be the question set. There are three other questions. I won't write them down. Let's discuss the question set. How many questions are there? How many questions are there? How many possible questions are there? Remember that a question, a binary question, whose answer is yes or no, is effectively a binary function that maps all inputs, some of them to yes and some of them to no. So the question of how many questions are there is tied to the question of how many inputs there are. Right? So how many different histories are there? A lot, I know. 100?
What's the domain?
Domain, okay, good question. Let's assume that the history stops at the sentence boundary. So it starts at the first word of a sentence and goes through halfway or somewhere through the sentence and stops. How many partial sentences there are?
So history of length n and vocabulary to the power n.
Right, so if we restrict history, let's say the history is less than 100 or even less, I don't know, 40, then the number of such histories would be the vocabulary size to the power of 40, right? That's a very large number. That's typically 100,000 words raised to the power of 40. That's 10, this is 5 times 40, that's 10 to the 200. Okay, that's how many different histories there are. Now, how many different questions are there over these histories? I'm sorry? 2 to the power of this number. Number of questions over the histories is 2 to the power of 100 to the power of 200. I'm sorry, 2 to the power of 10 to the power of 200. This is a doubly exponential number. It is really big. Don't make the mistake of converting that into a single exponent. It's not easy to do. But I guess you could somehow express it by saying that it's... I'll tell you in a minute, but just we'll take this number. This is 1 with 200 zeros after it, right? So, no, it's 1 with, 200 zero after it. So it's 2 to the... Excuse me for a moment while I goes on and on and on, okay? 2 to the power of that. That's a very, 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 very large number, really. How do they get that? So you should all know how to do that. That's not hard. In general, if you have a function from some domain to some range, if it's a discrete domain and discrete range, finite domain and finite range, although it actually generalizes to infinite numbers as well, but let's deal with finite numbers. if you know how many items are in the domain and how many items in the range, the number of such functions is the size of the range raised to the power of the size of the domain. In our case, the range is just yes or no. Right? It's a binary function. So the size of R is 2. It becomes 2 to the size of the domain. The domain is what we called X, or what we called here the number of histories, the 200. Another way to see why this is true, why it's 2 to the number of questions, is that every question can be defined in terms of what answer it gives to each one of the histories. So it could be represented as a bit vector of length 10 to the 200, such that each one of these bits is 1 if the question answers it yes, and no if the question answers it no. Now granted, of this incredibly long number of possible questions, the vast majority of them don't make much sense. And writing them down in natural language would not be feasible. You just have to say, for this history say yes, and for this history say no, and for this history say yes. I mean, you'll have to enumerate them. So they're not questions in the linguistic sense of things that make sense to us. But I just wanted to impress upon you that if you wanted to consider all possible questions, you couldn't even begin to do it. So we need to restrict the set of questions that we're going to ask. And we need to restrict it to a number that is feasible for us to iterate over. Let's say 1 billion, maybe a little more as computers get stronger. And we also need to restrict it to a number that is somewhat related to how much data we have. Because we're going to be estimating mutual information from data, and we're going to be restricted by that. So 1,000 questions is reasonable, 1 million is reasonable, 1 billion might be reasonable, 1 trillion, if you have enough computing power, I don't know. But that's still a tiny, tiny fraction of all possible questions. So the way to do that is now to switch from statistics to linguistics and say which classes of questions make sense. So the question is, make sense for what? Our goal is to create subcategories that would be the leaves, such that each of them will have low entropy, low conditional entropy. So the conditional entropy of the distribution of words, of the next word, given the particular history, would be as small as possible. Right? We would like to ask questions that split the data. For example, we would like to ask questions such that under some condition, it's very likely that we're going to get a noun next. And therefore, the conditional distribution of that leaf would have a lot of weight, a lot of mass on the nouns, and very little on the non-nouns. And some other leaf would have a large mass on the verbs, and another one might be on the adjectives. So you could think about it in terms of parts of speech. So that way we will reduce the overall, there's high entropy, there's a unigram distribution over all the words of the vocabulary, but under specific conditions in the history, we might be able to further restrict and suspect, oh, we're expecting a noun. Not just a noun, but a singular noun that's a concrete object. Or maybe I expect a determiner here. Maybe I expect a or the or an. That would allow me to reduce the conditional entropy of the next word. So what we're after, the beautiful discussion we had there of y and x's, y is the distribution of the next word, w. That's our, what we called y before. Maybe we should call it w. Big W is the random variable. And the difference between y and w is that y is binary, and w has 100,000 values. And the x's are all hidden in the history. The x's are different questions that can be asked about the history. So can you suggest some reasonable classes of questions to ask? Suppose you had to guess.
Does the history contain a verb?
Good. Does the history contain a verb? Does it contain a particular verb? So far I gave you examples how to in regard to part of speech, but you can also think of examples that come from topics. You know, if the history contains the word computer, maybe the probability of the word mouse should be higher. Mouse being the next word should be higher. If it contains, you know, baseball terms, you know, you can also put in topic information. Yes?
So to extend the topic modeling idea, if you could ask a question like, is there a subject that's already, does the history already include a subject? And does that subject fit into one of my known topics?
Okay. So you can ask a complex question that consists of a combination of different questions, as long as the final answer to that is either a yes or a no. Okay, that would work. All right, let's play the game. Suppose I'm asking you to guess the next word. That's an easier task than giving me a whole distribution of the next word. I'm asking you to guess the next word. What would be the first question that the first thing you would want to know about the history? What's the last word of the history, right? So there's a whole class of questions you might focus just on the last word of the history, rather than on did anything happen in the history. They're both fine questions, but it makes sense to also consider just asking about the last word, because you believe that that carries a lot of information, specifically a lot of syntactic information about what could come next. Now, I'm not allowed to ask what is the next word, because the answer to that is 1 of 100,000. But I can try through a set of questions to figure out what the last word is. So I can ask whether the last word is a noun or not. And if the answer is no, I can ask, is it a verb or not? And if the answer is yes, I can ask, is it a past tense verb? I can sort of work my way down in any possible way so that I can create like a mini tree that is all about the last word of the history. So I'm asking here about the last word of the specific question about the last word of the history, or called Q on W of I minus 1. And I don't have to, but I can, all of my other questions in the tree be about the same thing, such that in the end I have leaves coming out that each are specific to a particular, either a particular word in the vocabulary or some small subset of words in the vocabulary. And I can take this whole thing and use it as a component in my big tree that splits things up fairly finely based on the last word. And then at the end of each one of these, I can tack on another tree that looks at the next to last word, right? So in fact, I can reproduce a bigram or a trigram with a decision tree. If I wanted to reproduce exactly, to implement exactly a bigram with a decision tree, all I have to do is ask progressively more detailed questions about the last word, such that at the end I have 100,000 different leaves. And for each one of them, I know I'm conditioned on exactly that last word that occurred, and now I give the entire distribution of the word that follows it. So I can implement exactly a bigram.
Incredibly cumbersome. What are the
Yes.
advantages?
There is not much advantage in implementing an n-gram in a decision tree. If all you want is an n-gram, you don't need that. What I'm pointing out is that decision trees are very expressive, and that as a special case, they include all the n-grams. So any n-gram can be expressed as a decision tree. The opposite is not true. There are decision trees that cannot be expressed as n-grams. In fact, the vast majority of them cannot be expressed as n-grams because they ask the kind of questions that n-grams cannot ask. But one practical reason for showing that they are a superset of n-grams is to say that are there decision trees that are better than n-grams? Probably, because we know that there are definitely decision trees that are as good as n-grams because they are n-grams effectively, and there could probably be, very likely be, trees that are even better. So this is to make us realize that the space we're searching in, the space of all trees, is strictly larger than the space of n-grams. Strictly larger is not necessarily better, because it's a bigger space that's hard to search in, but it has better potential. Oops. Thanks for the cues. I'll let you go.